today and their webinars earlier this morning over in Europe. I want to thank you guys for joining our session today, and we'll hope to round this day out with some good tips and tricks for ICP analysis. So before we get started, I want to introduce Thomas Kozakowski. Thomas is our field applications chemist, and we're going to do this webinar a little differently today. So if you have any questions at any time, please use the Q&A box in the Zoom meeting. So if you click under, it might be under More, and then you should be able to see the Q&A box. So if you have any questions about any of the material at any time, go ahead and enter your question. And Thomas is going to answer your question directly over text, and you guys can follow up back and forth as you wish if you need more details or anything like that. So Thomas is going to back me up today and handle all the Q&A parts. And then I will also give both contact information for Thomas and I. That'll be the very last slide. So if you have additional questions afterwards, you can always email out to us and we'll be happy to answer any questions you might have. Additionally, this webinar will be available on demand. Give us about a day or so and you can check the Inorganic Ventures website. If you look at the education tab and go under technical videos, this webinar should show up there. And again, I would expect that would show up about sometime tomorrow. So give us about a day to get that posted. But if you want to go back and listen to any part or again, see that contact information, ask us questions, that information will be stored there. All right. Well, thanks again for joining us. I'm going to go ahead and share the presentation. And Thomas, just let me know if this isn't working. But I'm going to go ahead and start things off. So like I said, my name is Mike Booth, and today we're going to talk about tips for trace analysis by ICP OES and ICP Mass Spec. I am the Innovation and Applications Development Manager here at Inorganic Ventures, which is just kind of a fancy way that we say research and development. So my team handles new products and also our custom products. If you're not familiar with Inorganic Ventures, like I said, if you're joining us from the CEM and glass expansion sides of the sessions this morning, just a brief introduction to what we do at Inorganic Ventures. We are a manufacturer of mainly inorganic certified reference materials. With a name like Inorganic Ventures, you expect we just do metals. We do a few organics for ion chromatography, but just a few. But if you have any questions, just reach out to us. Along with metals for ICP, OES, and mass spec and AA and any other technique that you need metals to analyze for. We also do standards for pH, conductivity. We do certified titrants. We do reagents. We do a lot of different things, including custom products. So if you need a custom standard manufactured, we are your partner to do that as well. So if you have any questions, please visit our website. You can see our full product catalog on our website. And reach out to us if you have any contact information. But this is essentially what we do. And a big part of what we do is we focus a lot on our educational resources. I mentioned our website in the introduction. Our website is chock full of helpful tips and tricks. I would recommend our interactive periodic table. That's probably our most popular resource. And yeah, explore our website. Reach out if you have any questions about what we do. But let's dive into today's presentation. So today's presentation is actually kind of a mix of some of our top topics that we cover when we do these types of webinars or seminar speaking events. So we're going to cover environmental contamination, solution matrix, washout issues, and uncertainty of measurement. So these are kind of four topics that always kind of get brought up whenever folks are wanting to discuss ICP, OES, or mass spec. So we're going to dig a little bit into the details on all these. But again, like I said in the beginning, if you have any questions, please feel free to ask. Use that Q&A box, and we'll get those answered for you this morning. All right, so container selection is first up. So there are lots of different types of containers that you can select to hold your sample or hold your standards or your working standards. So which is the best type of container to use and what are the concerns? Well, the big concern is contamination, right? This section's all about contamination considerations. So how do we control for that? And your container selection has a huge impact on that. So generally, plastic is always going to be cleaner than glass. If you are storing your samples in glass, you're probably introducing a lot of contaminants you may not realize. But there are some reasons why you may have to use glass as your container. So Of the plastics, typically you're going to run into LDPE, HDPE, PTFE, PFA, some of the fluorinated compounds, Teflon, polypropylene. You also want to look at if you're using sample tubes versus bottles. And what we found is generally bottles are a little bit cleaner than sample tubes. But the good thing about plastics is you can leach them all with dilute nitric. And what we found is that high temperature leaching is more effective. So if you're able to leach your containers at about 50 degrees C for a few days, rinse them out, they're going to be a lot cleaner than just using them straight out of the box. So we'll talk about how we clean our bottles at Intergang Ventures here in a few slides. This next slide goes into kind of what contaminations you can expect to see. And this table is all broken down on the nanograms of impurity per a 125 ml bottle. So LDPE has our blue ribbon here because it is our top choice. It comes out a little bit cleaner out of the box, and you can leach it out really, really well. But here are some of the levels of contamination you can expect with these bottles. So LDPE, you're going to expect to see a little bit of aluminum, magnesium, sodium. Again, you can leach these containers and get them very, very clean. HDPE, expect to see more calcium and iron. Polypropylene, magnesium number is what we've seen a lot. PTFE or Teflon, those are actually really, really great bottles. They clean up really well, but they are very, very expensive. So that is the biggest downside. If you guys are purchasing trace analysis grade acids that come packaged in Teflon bottles, I would highly recommend that you don't throw those away. Hang on to them. They do come in useful in various situations, and it's an expensive material, so it's always a shame to waste those bottles. And then in the very last column, you can see borosilicate glass there, just large numbers of impurities covering, pretty much every element we decided to put in this table. And you're not going to be able to leach that stuff out either. It's going to continue to come out of the glassware. So that is really one of the big downsides of using borosilicate glass. Although if you're doing trace analysis mercury, you may want to use glass over plastic. All right, so I talked about leaching. So leaching observations, unleached bottles are going to contain the metallic impurity, but you can leach them to pull that stuff out. So again, I mentioned at the beginning, hot solution is going to essentially pull those contaminants out a little bit better than just room temperature leaching process will. But room temperature leaching is what we do on the majority of our bottles. The next couple slides, I'm going to go into that process and kind of describe how you can do that for your containers in your laboratory. We've looked into chemical dishwashers before, but what we found is while the chemical dishwashers may be plastic in the area that you place the bottles and where the rinsing is happening, a lot of the tubing, the plumbing has stainless steel parts that will transfer contamination back into the containers. So you really have to be careful about that. That's why we recommend against using a chemical dishwasher. We've not been able to find one that was completely free of metallic parts. So if you are interested in leaching your own containers, and this is how we leach our bottles, but it's a very similar process for tubes, for basically anything that makes contact with our standard can follow a similar leaching process. So first up, you need to make a leaching solution, and you pre-make 1 to 5% nitric. That nitric doesn't need to be a really high purity nitric acid. It can be your stock nitric acid that you want to use. You're not really overly concerned about the cleanliness of the acid, just that it's acidic and it's going to pull those contaminants out of the bottle. Uh, because we bleach so many of these bottles at a time, we use automation, but for years we did this by hand, so it's more than feasible to do this by hand. But we use automation to stand all the bottles upright and to fill the bottles up. So you want to make sure you fill that bottle completely up and then cap it. And then what you're going to do is let those bottles set at room temperature for 7 days or 4 days if you increase the temperature to 50 degrees C. So if you want to save a little bit of time and get a really good leach on those bottles, you can increase the temperature by putting them in an oven. And then, yeah, you can take them out 3 days early. After that, this is critical. You need to make sure that you rinse those containers really well. So rinse them out at least 3 times with deionized water. Um, Make sure you're doing full rinses, filling the bottle up, emptying it completely, filling it back up again. Make sure you rinse all that acid out of that bottle. And then You can dry them and they're clean for general use. Just make sure that when you store those dried bottles, you're keeping it somewhere that protects it from other environmental contamination like dust or something like that. So we use large plastic bins that have lids on them. You can find something very similar, but that's how we store all of our pre-cleaned bottles. And then as we need them, we just pull them. We know that they're leached, that they're going to be good, that we're not going to transfer any contamination from the bottle to our sample or to our standards. So speaking of environmental contamination, that is another big area that can be of concern when you're doing trace analysis is again, how do you prevent all this contamination? You can look into getting a clean room if you're working at very, very low concentrations, so something like PPT concentration range. There are several criteria that you need to look at when you're sort of designing or wanting to set up a clean room. Everything, the airflow is a big one, but everything from, where the air return, where the HVAC system air return is, the type of ceiling material, the types of light fixtures, all that stuff can go into it and have a big impact as you're trying to set up, particularly a classed clean room. So this is something that if you don't want to set up a classed clean room, you just want to set up a cleaner room as part of your laboratory to perform this trace analysis. You can still look at these criteria as something to help you out with as you're selecting the best materials to put that room together. So again, this table here just kind of shows you the different classes of clean rooms. Um, you can use it for reference. I'm not going to go through this whole table with everybody, but this is just kind of what is used for reference. And one of the things that I will recommend is you can get a pretty cheap particle counter, like an air quality particle counter. And this is what we've done as we've made laboratory improvements at our facility. So we'll take measurements, for a few days at different areas of the lab before we do some sort of infrastructure improvement, and then we'll measure the impact afterwards. So one of the big things that we did this on was we changed out our ceiling tile type. Our ceiling tiles in the lab years ago were that kind of plastery material that was kind of brittle. So if you kind of, touched it or rubbed it, it would break apart into little pieces. We changed that out to a more plastic, solid ceiling panel. And we took measurements before and after we did this. So, and what we found afterwards was after we changed out to the new ceiling tile, that particle count dropped considerably. So that was evidence that we had kind of said, yes, this is a good change to make. We're seeing less contamination. And in general, we saw less dust in the lab after changing out also. So just something to keep in mind. I think that's what I would recommend if you're not going for a fully classed clean room, just get a cheap air quality particle counter and take some measurements before you do any infrastructure improvements, and then just take measurements afterwards so you can get kind of a gauge for how well you did. It's better than nothing, but again, it doesn't compare to the class clean room. If you need a fully class clean room, then you'll probably want to go with, a construction group that is really specializes in how to do that. All right, last thing to touch on in this contamination section is just about reagent purity. So I mentioned before, you don't have to use a clean acid to make that leaching solution. You do need to use a clean acid if you're doing digestions on your samples, clean bases. Clean DI water is a necessity. So you need to think about things too if you're this kind of gets steps outside the bounds of ICP analysis. But if you're doing anything that's sensitive to like ammonia or something like that, having clean water is just super, super important. So no matter what you use, I always recommend that people do run reagent blanks as well, because you need to, if you don't have access to the cleanest purity acid for your digestion, uh, try to quantify how much contamination you are adding through the use of a reagent blank in your method. So that way you can blank subtract, and it helps determine the true levels of impurity that you're seeing, and also helps you with your detection limit as well. All right. Next section we're going to talk about is solution matrix. So this comes up pretty frequently. I mentioned that we do custom products, so putting together custom standards for folks. How do we know that that custom product is going to remain stable in the bottle and not form precipitate or not have issues over time? So this is something we look at and we monitor all the time. We have I think, some pretty great tips and tricks for folks. So when it comes to solution matrix, most people want to use nitric acid, especially if you're using ICP mass spec, because they want to avoid that potential chloride interference. So the good news is most elements are stable using nitric acid, but some of the elements in nitric acid matrices will require hydrofluoric acid for stability. So if you have to add hydrofluoric acid, that's where, again, we really starting to get in the danger zone in terms of glassware. HF is going to attack the glass. HF can have instability issues with other elements. We'll talk about that in the next slide. So once you start adding HF, that's where things start to get a little more complicated. But again, it is necessary for some elements that need it. If you can use HCl, a lot of elements are really happy in HCl. A couple will have issues with it, and we'll talk about that in more detail. But again, if you're using ICP OES and you're not worried about chloride interferences as opposed to ICP mass spec, then hydrochloric acid is a really good matrix. And we're going to show, again, next couple slides, you'll see that. If you're trying to measure bromide or iodide, that's where you really want to stay away from acidic matrices and switch over to basic matrices. You can get some of the other metals stable in a basic matrix as well, but bromide and iodide are really where you have to be careful. So let's dive into each of the matrices and start going in through them one by one. All right, so here is our periodic table. Again, like I mentioned before, all the slides and stuff will be available on demand. So if you want to go back and reference these, feel free. You don't have to make notes of everything right now live. But here, if we're looking at just the solution matrix of nitric acid and HF, what these slides kind of correspond to is anything that's not highlighted by that legend there underneath the title. Those are all going to be fine. For the most part. So you don't have to worry about things like chromium or magnesium or iron. They're fine. But we really wanted to highlight some of these other elements, like the yellow elements at first. So when I mentioned hydrofluoric acid being needed, these are the elements in nitric acid that need to be stabilized with hydrofluoric acid. So you have that block there with titanium, zirconium, and niobium, molybdenum, hafnium, tantalum, and tungsten. And then you have that block with silicon, germanium, tin, antimony, and tellurium. So those absolutely will require HF in nitric acid to remain stable. Now, where that comes as an issue is all the elements in red. So your group twos, your magnesium, calcium, strontium, barium, you have your rare earths there at the bottom, and then you have scandium, yttrium, and lutetium. All of those have some compatibility issues with HF. Depending on the concentration, you can form insoluble fluorides. So it's depending on the concentration, again, of those elements that have bad interactions with HF and the amount of HF that's in solution, both play a major part in it. So if you want to have, high concentrations of some of these HF elements, you can't put high concentrations of the red elements together in the same solution. You're going to form precipitate almost immediately, and the solution is not going to remain stable. So that's pretty straightforward and easy to work around. The harder part comes into these elements in beige that we've called the HF thieves. So what happens with those is in nitric acid alone, they don't require hydrofluoric acid to remain stable. But they do have a very strong affinity towards that free fluoride in solution or the fluoride in solution from HF. So what can happen is they have such a strong affinity for it, they can actually pull it away from the elements that need it to remain stable. So if you start adding in a lot of aluminum, for example, into your standard or into your sample, but you do have concentrations of niobium or tantalum, it can pull that HF away from the ones that need it, and it will destabilize those elements that need HF. So to get around that, you have to spike in extra hydrofluoric acid to account for the HF that's going to be taken away from the ones that really require it. So this is where it starts to get a little bit more complicated. So this is why you may have limited stability when you're starting to mix different pre-made stable blends of solutions together. It's because you might be introducing some of these high concentrations of elements that really require that, or not require, but have a strong affinity for hydrofluoric acid. So if your matrix and you're trying to matrix match has high concentrations of aluminum or phosphorus or sulfur, that you're just trying to get a good matrix match on, you may be unintentionally destabilizing some of the other elements because you're introducing an element that really pulls HF away from the ones that require it. All right, let's look at HCl. So HCl, um, like I said, a lot of things work very, very easily with HCl. So I'm going to talk about the ones in blue at first because those are the ones that typically most people want in HCl matrices, your precious metals and mercury. Mercury is a weird one. A lot of folks will prefer mercury and HCl because at lower concentrations, you can get mercury and HCl to be good and fine in a plastic bottle. So again, kind of touching back into that contamination issues before. If you want lower concentrations of mercury and nitric acid, you need to switch out to a borosilicate glass bottle, which again could introduce potential contamination. So we'll kind of group mercury in with the precious metals. HCl is what you want to keep those in for the most part. Now, the green elements are really kind of interesting because in nitric acid, they require that fluoride ligand to remain stable in solution, but in HCl, they don't. So you can, if your lab is not allowed to work with HF, but you still need to measure titanium, zirconium, tin, antimony, or tellurium, you can use an HCl matrix and get away from hydrofluoric acid at all. So you won't have to use it at all in your process. That's a really good kind of workaround for those HF free laboratories. Now, the ones in red are the ones that have precipitates that can form with the chloride from the HCl, right? But the good news is that every one of these elements in red have a workaround for them. So silver being the most, well-known issue. Of course, everyone kind of knows silver chloride is going to fall out of solution. But if you add HCl in excess, and major excess to the amount of silver in concentration, you can actually stabilize the silver in solution and it will remain stable. The solution will be photosensitive, so you have to protect it from light, but the silver will stay in solution. And when I say excess, what the general rule of thumb that we use is for every ppm of silver, 1%, the corresponding percent of HCl. So for example, silver at 10 ppm, we put that in 10% HCl, silver at 20 ppm, 20% HCl, and so on. So eventually it gets to a point where it's really not feasible because you have such a high concentration of HCl. But again, you just have to have that chloride in major, major excess. For thallium, it's all about the oxidation state. So thallium plus 3 is going to be good for HCl stability, where thallium plus 1 is going to fall out of solution. And then for lead, it's all about the concentration. So concentrations less than 500 ppm are okay in HCl. Above 500 ppm, you can start to see issues. You might form a precipitate. So the thing about HCl that's really good is there are elements that have issues with it, but again, you can work around all three of those elements. So let's look at basic matrices. So a basic matrix could be, a regular base like potassium hydroxide, sodium hydroxide. You could use triethanolamine or what we call T or ammonium hydroxide and water. So the basic elements I mentioned at the very beginning of this, bromide and iodide, those need a basic matrix to do your analysis. What's going to happen if you try to use an acidic matrix, especially with things like bromide, you'll probably start to see your tubing turn red. That's kind of an indication that you're not going to have a very good analysis. So stabilize those elements in basic matrices is going to work out better. There are some other elements that can work with basic matrices as well. So things like boron and arsenic are going to be fine. And then also interesting enough, some of the HF elements in nitric acid matrices, again, will work in basic matrices. So things like silicon, molybdenum, and tungsten. Again, if you are running an HF-free lab, and depending on what your samples are, you may be able to get away from HF if you need to measure those elements. All right, next up. So multi-element compatibility. We talk a lot about concentration and how important that is to really create a stable solution. So how many things can we put together in one solution at different concentrations? So this is kind of a guide, a rough guide. There are lots and lots of different variabilities that can happen and issues that can come up. But as a rough guide, at 1,000 ppm, let's take a look at the HCl ones first. So all your precious metals, they're going to be fine, 1,000 ppm and 10% HCl. All of the other elements there, so the ones in the more reddish color, you can put those all together at 1,000 ppm. You just really need to increase that nitric acid concentration. So you have to increase the nitric acid concentration up to 15% nitric. And then if you want to start adding in these HF elements, you can, but you have to increase the amount of HF in your matrix. So up to 3% HCF or HF to get those elements in solution. And again, that's all going to kind of vary depending on how many you want to put in the same solution. But in general, you can get all these things together. You just need to make sure that you watch out. And again, if you're trying to add them all together, you might have HF issues. So in theory, all the ones in red should be fine. And then we would split all the ones in green out separately and put them with increased HF concentration in the matrix. But if you have room to sort of work on that concentration and bring that concentration down, you can see in this slide, you can get a lot more things to play nicely with each other. So at 100 ppm, you can drop that nitric concentration from 15% down to 5 to 10% nitric. You can bring in some of those HF elements that we had to split out completely before. You can bring them in with trace HF that should work out fine with some of the more HF sensitive elements. And again, there's only leaves a few of the HF elements out there that you really want to split out and then bump up the HF concentration. So the ones that really need it, like niobium, tantalum, and tungsten, that's where you're going to want to split it. But again, at 100 ppm, you have a lot more options on things you can put together. If you drop the concentrations even further, so if you're doing ICP mass spec work and you're really looking at a bunch of elements at low concentrations, this is what you can do in nitric acid at 10 ppm. So in 10 ppm, you can pull everything essentially together in the same solution. Trace HF, you're not going to have instability issues because of HF and the HF sensitive elements. You can also, at 10 ppm, if you wanted to put silver in your precious metals mix, you can, because that's 10 ppm silver, 10% HCl. So again, that blend would be photosensitive, but it would be stable. So you can get a lot of things to play together at 10 ppm and nitric and have a really good solution. If we switch the matrix up to just focus on HCl exclusively, you can get basically everything together and at 10 ppm and 10% HCl. You can roll your precious metals into the others. The only issue that you will have, and we've seen on occasion, is issues with platinum and either cesium or rubidium. So cesium or rubidium can form this platinum hexachlorate compound or hexachloride compound. That is going to form this precipitate. It shows up on occasion, so we would split out the cesium or rubidium for that. But again, those are elements that are not really requested very often with all the others. So again, HCl at 10 ppm, 10% HCl, you're going to be fine. There'll be a little bit of trace HF in the matrix from some of the ones that really need it, but you're going to have a good solution in that as well. All right, so next section for this morning, we're going to talk about washout issues and how poor washout can lead to inaccurate results. So what are the causes for washout issues? And we just talked about the compatibility of the elements and how important that is to make sure you have the proper matrix for the proper element mixes. A lot of the issues around washout is kind of the same boat. You're introducing a rinse solution that might have an issue with the samples that you're running in between the rinse solution. It can also be an issue of specific elemental affinity towards the plastics. So again, I've kind of mentioned mercury a couple times about how at low concentrations you want to store it in glass. That's because what can happen is mercury has a strong affinity towards plastics. You can see it stick to the plastic materials of the bottles, but you can also see that happen to the pump tubing in your ICP system. Another big source of washout issues is spray chamber design. So the folks at Glass Expansion, if you're following along today as part of that joint webinar session, I'm sure they talked a lot about spray chamber design and how that can improve washout. So typically, the smaller the spray chamber, the more you're going to see an improvement on that washout. And again, I mentioned rinse protocol, so using the incorrect acid or base, and then also just the amount of time it takes. So, always keep in mind as you're designing your ICP method how long your actual solution is running through the system. So in theory, if you have a long uptake time, a long analysis time, that's just more volume of liquid sample that you're pumping through. It's more opportunity for things to stick around. So if you can limit that amount, in theory, you should improve washout at the same time. So let's pull out another periodic table here. And just these are the elements that we've identified that can have issues with washout. So a lot of folks talk to us about gold washout as well. Typically, that's because they're just not using HCl rinse. I always like to mention that in there as well. But you can see some, if you remember back to the first periodic table in the last section, what you see is a lot of these elements are the same as the nitric HF HF required elements. So typically what happens is in your sample, you might have hydrofluoric acid, but in your rinse solution, most people don't rinse with HF in that rinse solution. So that can be a reason why they kind of tend to have issues with washout or might take a little bit longer to wash out. Um, and again, same thing. Silver can be a little bit sticky. Um, if HCl is present, especially at low concentrations, you might have issues with that. But a lot of it is just dependent on the the actual chemistry of your rinse solution, and some of them is dependent on the affinity towards the plastic. So some things like bismuth, for example, is one that's it's really sticky. It seems to stick to particularly the PVC pump tubing. If your sample is running through PVC pump tubing around the pump of the instrument. So that's just an area that can kind of hang out. So it's mainly the chemistry or the specific affinity towards the plastic tubing. So some common rinse solutions. Most people use some dilute nitric, so either 5 to 10% on OES or 1 to 2% on mass spec, or HCl, depending on their method and what they're using as their main diluent. So if you're prepping all your samples in nitric, you're usually rinsing out with nitric, and vice versa. Vice versa. If you're prepping all your samples in HCl, I would suggest you have your main rinse be HCl. Water can be really effective as a rinse solution for things like sodium, potassium, calcium, your group ones, your group twos. That can rinse out really, really well with water. So if you have high concentrations of those group one, group two elements, you can throw in a water rinse and be fine with that. We always like to end our we call them batches, but essentially as we finish running all of our samples, we run a dedicated rinse protocol to make sure we do a really good rinse of the whole system and try to get it set up for the next batch. Water is always a part of that. And then so is RBS 25. So RBS 25 is a laboratory detergent. You make a 2.5% solution of this and you can aspirate it on ICP OES. We don't recommend doing this on mass spec because it has a high concentration of sodium that is present that might take a while to rinse out. But you can aspirate this on OES. And again, it does a really good job of kind of refurbishing the system for your next batch or your next set of samples. And again, after that, we always rinse out with water since it has high concentrations of sodium. We run water after we run RBS 25. It helps rinse that sodium out of the system. All right. So I mentioned before, some of the elements that are sticky are also the elements that require HF to remain stable in nitric acid. So if you are using HF in your rinse solution, you just need to be careful of a couple things. I would limit the HF to a maximum of 0.2% if your intro system is glass, if you have glassware in your intro system. And just keep in mind your boron and silicon results will probably be unreliable, and you're probably going to damage those system components over time. We've done it in the past, but what can happen is you can start to etch, especially the spray chamber, and it won't wet as properly as it should. So if you just have a batch of samples you need to run as a one-off, it may not be worth it to purchase a whole HF resistant system, especially if you don't care about boron and silicon results. But just keep in mind that after you run HF through a glass system, you want to really take careful work to refurbish it as best as possible and do everything you can to limit that HF that's running through there as best you can. Now, if you switch over to an HF resistant nebulizer spray chamber, then you go by the manufacturer's protocols of what they say. The example I posted here is a spray chamber from Glass Expansion that has a coating. They're kind of moving away from that now. So some of the better designs seem like they're switching away from that coating. And you can on that if you're using the system with a coating, you want to limit the HF to a maximum of 3%. That's because it can start to eat away at that coating a little bit faster. And again, you'll see issues with performance, but HF resistant systems are really, really good. And a lot of times you're not running many samples that have that high concentration of HF, unless you're running very high concentration samples for some reason. So let's talk some specialty rinse solutions. Again, I kind of mentioned before, if you're running bromide iodide, you'd want to switch over to a basic matrix. So again, you'd also want to switch over your rinse solution to that as well. So ammonium hydroxide rinse can work out really well for both OES or mass spec. And what we found is it can also be a good rinse for some of these elements like boron or mercury that might stick around, including bromide and iodide. I will recommend for this if you are running your samples in an acidic matrix, um, and you want to use a basic rinse, also do a follow-up rinse every time with water. So you're not running a basic rinse and then running acid right after it. Try to put a water rinse as a buffer in there as well. HCl hydroxylamine hydrochloride. So this is something that we found is going to work really well if you're focusing in on precious metals analysis. So this was a matrix that we had found in our lab's work with osmium that works out really well. It seems to work out for all the precious metals. So again, it's just kind of a specialty rinse solution. Just want to throw it out there. And then one of the older ones that works out really well is a mixture of HCl and thiourea. So this is really useful for laboratories as well. So this has been known for a while. We actually sell a mixture of HCl and thiourea. We call it ICP True Rinse. And in this slide, you can kind of see a washout study that we did on ICP OES, comparing ICP True Rinse to some of these standard and specialty rinse solutions. So we looked at gold, bismuth, mercury, and osmium just to sort of see, as we run high concentrations of this through, how long does it take to essentially go back to baseline with our rinse solution. So you can see ICP True Rinse performed extremely well with all these elements. Some are closer than others. So if for instance, if you look at bismuth, 10% nitric and ICP True Rinse were coming very, very close. But if you compare that to 5% nitric, 5% HCl, and ICP True Rinse for bismuth, you see a big, big difference there. Same thing for osmium, same thing for mercury. Mercury, you can tell in this slide, had a lot of data points that were pretty high time-wise. Again, to get back to full baseline after introducing a high concentration. So that mixture of HCl and thiourea can really be helpful. Just again, it contains thiourea, so thiourea contains sulfur. So that is just something to keep in mind as well. So if you are trying to do trace level sulfur analysis, it may not be the best, but this is something that we recommend having on hand if you need to prepare your instrument to get ready for a different analysis. All right, so troubleshooting washout issues. Again, it really comes back to identifying the elements that give you trouble. So what I recommend is, as you start your analysis, run a couple blanks through the system. One, to get the system, make sure everything is working correctly, but also gives you a baseline to sort of see like, all right, well, at the beginning of the run, my counts for these elements were X. And as you start to run your standards and samples, and you start running maybe other method blanks or just blanks throughout your run, you can kind of compare that and see if you're experiencing issues with washout or not. If you keep up with routine instrument maintenance, that's another big one. So make sure that you're doing your maintenance when needed. Again, I would highly recommend putting in place a really thorough rinse protocol at the end of all of your batches. So your groups of samples, we found that helps out immensely and can help save some time on instrument maintenance as well. So it's really just kind of monitoring what's giving you washout, compare it to what keeps that element stable in solution. Do you need to switch out your method rinse solution for something else that might have a better affinity towards that solution to help it, get picked up and carried through the system? And then keep up with instrument maintenance, and that's going to be the best way to troubleshoot washout. And again, your sample introduction system can have a big part to play in that as well. So if you're struggling with it and you just can't find a solution, talk to the folks at Glass Expansion. They'll be able to help you out. Whoever you're working with for your instrument, your sample introduction system, they'll be able to help you out and select maybe a better spray chamber to improve that washout as well. All right, so this is going to take us into our last topic for today, and that's going to be uncertainty of measurements. And really, we're going to discuss what is a reasonable uncertainty of your analysis and how can you take any steps to improve it. So the first topic is how low can you go in terms of this uncertainty? And this is where you need to review the relative uncertainties of your standards that you're using because that really sets your baseline. So for us, our standards of comparison that we use that we trace all of our results back through is NIST SRMs. So this is an example of a certificate of analysis of a NIST SRM. This is for silver. So you can see this solution of silver that we receive from NIST has a concentration of 10.007 milligrams per gram with an uncertainty of plus or minus 0.019 milligrams per gram. So if you essentially divide the uncertainty by the certified value, multiply by 100, what you get is about a 0.2% relative uncertainty for that CRM, or for that SRM. So if we make a standard and trace it through this NIST SRM, we can't realistically have an uncertainty that's less than 0.2% relative to this because this NIST is setting our baseline. So if someone is, tracing uncertainty back through their standard and somehow their results have a lower relative uncertainty than their standard is, then something has gone a little wonky. So that sets your baseline. Then you really want to look at all the areas as part of your method that introduce error. So sample preparation comes in first, right? So this is something that a lot of folks do. We always recommend folks prepare preparation by weight, but it's not feasible in some laboratories where the throughput is just extremely high. So we put this together. This example is kind of like, okay, let's look at the error in preparing by volume versus preparing by weight. So we took a 1 milliliter aliquot calibrated by an electronic pipetter, dispensed by a calibrated electronic pipetter. That has about a 0.3% relative error on that measurement. If you compare that to preparing by weight, a 1 gram aliquot on a 4-place balance, you see, a big improvement on that relative error. So by a factor of 10, we go from 0.3 to 0.03% relative error. But a 3-place analytical balance is right in the same ballpark as that 1 mil calibrated electronic pipetter. You're at 0.3% for that versus 0.2 on a 3-place analytical balance. What you don't want to do is take a 1 gram aliquot and weigh it on a 2-place analytical balance, because then you've got a very big error compared to preparing it by volume. So 1.5% relative error versus 0.3% by the pipetter. So these are the things to kind of watch out for. Again, we always recommend preparing by weight, but it always depends on your laboratory setup. If all you have access to is a 2-place analytical, you may not want to prepare it by weight. You may want to use the pipetter instead. It might actually be a better solution for you. So again, like I said, we always recommend preparing by weight if possible. If this is a possibility for your lab, especially when you're preparing your standards, you can always use the density of your standards to switch back and forth between micrograms per mil to micrograms per gram. Do your analysis. You can convert back using the densities. Just make sure you track the uncertainties. If you do the same process with your samples, you'll need a density of your sample. So make sure you're taking into account the uncertainty from that density of your sample as well. All right. Instrumentation is up next. So instrumentation is where you can have definitely some error come in. The biggest place to sort of look for instrument error is look at your percent RSDs of your measurements. So that standard deviation of the replicates that you're measuring. So typically on OES, people will use 3 to 5 replicates. So every time they go to measure their sample, they're actually measuring it 3 or 5 times. On mass spec, that number can vary wildly. So, whatever your RSDs for your measurements are, go ahead and take a look at that and try to get that number as low as possible. So one of the best ways to do that is really inspect the sample introduction system extremely well. Double check the tightness of the tubing connections. Monitor your sample. One of the things that I like to do the first time I press, essentially hit go on the instrument, I'll watch it run the first sample and make sure that, you can see where the sample is moving through the introduction system. Make sure that it's reached the plasma by the time the uptake delay is finished. So that stabilization delay in your instrument, it's in the plasma, it is stabilizing for that whole period. So just make sure you're watching all those things because that can lead to, if your instrument timings are a little off, that can lead to issues with your percent RSDs. Another way you can improve error is by matrix matching. So having your standards and your samples in a similar matrix can help stabilize nebulization efficiencies. So keep that in mind as well. That way, if your nebulizer is running standards at maybe a lower density sample or standard versus a higher density sample, you can keep that in mind. You can see some issues there. Total dissolved solids is going to have a big impact on things that not only does it introduce a lot of interferences, that could have issues with your accuracy and precision, but it just can have impacts on the nebulization efficiency as well. So, speaking of interferences, matrix matching is a good way to get around that. But just keep in mind any contaminants that might have been introduced during the sampling or storage of your samples or your standards. So, again, just double check anything that makes contact with your sample or your standard. So everywhere from sampling through preparation through analysis, just really inspect anything that's going to make physical contact with that sample and just see if it's free of contamination. And the last thing I'll mention on this is just be mindful of interferences that may be present in your calibration standards, but are not present in your samples. So this is something where you can get a really well-designed method. But what happens if your samples that you're running, they're most likely unknowns, but what happens if they don't contain an element or two that are in your sample set or in your standard set? Will that cause interference or will that lack of potential interference cause any issues with your sample results? So it's something to keep in mind and just double check. All right. So limits of detection is another big issue that we talk about as well. So just keep in mind that anytime you're measuring near your limit of detection, expect to have, not as good accuracy, not as good precision because you're measuring near where it's just really difficult to tell the difference between if there's something in your sample or not. So method detection limit reviews, just, what you want to do to calculate that is construct your calibration curve and then run a series of method blanks after that. And what you're going to do is you're going to run, maybe 10 method blanks. You want to do a student t-test. So you'll pull up your t-value, multiply that by the standard deviation of your method blanks, and then multiply that by your dilution factor that you use for that method blank. So if you're, or for your samples, whatever that's going to be. So if you do a 10x of your samples, multiply it by 10 at the end as you're calculating your method detection limit. So again, it's the detection limit of your sample post dilution, not including dilution. That's a really important designation to make. So to lower your method detection limit, if that's the calculation there are a couple things you can do to impact that. You can try to improve the sensitivity. So to do that, that's going to improve the overall signal to noise ratio. That's going to reduce variability in your blank measurements. And to improve sensitivity, that's where you really want to hone in on your sample introduction system. So maybe you need to use a different nebulizer that's more fit for your sample type. Precision, if you can lower precision or increase precision, then you can lower that standard deviation of your method blanks, which is going to give you a lower method detection limit overall. So if you can get a more stable measurement, again, look at your sample introduction system, look at your whole setup, see if there's anything that's generating any sort of issues with precision, and then look at your dilution factor as well. Sometimes you can't get away from diluting your sample out. Sometimes you may be able to do, instead of a 100x dilution, maybe you can do a 50x dilution factor. What you may have to do as part of that is just to make sure you're properly matrix matching your standards to account for that. But it is a possibility you might be able to get away with a lower dilution factor, and that can decrease your method detection limit. All right. So just to kind of summarize this topic here, largest contributors to uncertainty for ICP measurements is going to be the look at your standard of comparison because that's going to set your baseline. You can't go lower than that. So if your standard that you're using has a high relative uncertainty, you can't expect to have a better uncertainty of your analysis than that. Watch anytime you do measurements of small weights or volumes, make sure that those are very accurate and are using the best equipment possible for that, because that's going to be the next biggest thing that's going to introduce error and contribute to uncertainty. And lastly, anything you can do to control those instrument RSDs is going to just help improve. It's going to give you a better detection limit, one, but it's also going to give you better uncertainty in your measurements too. So that's where really sample introduction systems come into play. Making sure you're doing good maintenance to your system. Really, anything you can do to lower those RSDs is going to help. And if you're interested in more information about uncertainty of measurements, have some resources here that you can look into. There's a lot of interesting resources about this out there. But yeah, that pretty much concludes this. So I do have a couple things to share before we sign off. Looks like we're right on time, and I'm going to use this as another opportunity to say if you do have any questions, please enter them into the Q&A box down below. Thomas has been answering questions throughout. But if you have any questions, now is kind of your last chance to get them in. And then in the following slide after this, I'll have our emails on screen if you want to email us directly as well. So yeah, please take this opportunity to get your questions in as I kind of review some of the other resources that we have available for folks at our website and other places. So our website, as I mentioned at the top of the webinar, is a really great resource for folks. Please check it out. It's inorganicventures.com. You can go to that education tab at the top, and we have an ICP operations guide. We have a trace analysis guide. We have tons of sample preparation guides. I mentioned the interactive periodic table. That's a great one. Just so many webinars, video resources you can find on the website, blog posts. It's a really good stuff, and downloadable ebooks as well. Our marketing team has been doing a great job, specifically if you're in the mining or pharmaceutical industries. We have downloadable ebooks that kind of summarize all of our best resources targeted to those industries specifically. Download those and get those out to whoever needs it in your lab, and I think you'll find some good resources there. We do a podcast. So we do a weekly podcast called Bench Boost where we talk over just any number of ICP challenges, but not just limited to ICP. We talk ion chromatography, titrations, pH, anything like that. So new episodes of that release weekly. You can download that. You can also find that on our website, or you can scan that QR code. It'll take you there. But you can download those through your podcast apps. And then finally, IV Ignite is our virtual training academy that we've put on. So yearly we do an ICP conference hosted at our facility in Christiansburg, Virginia. We took part of those courses and put them online as well. So there is a free version of IV Ignite. You can sign up, take some free courses. And then if you want to move beyond that, there are courses as well. You can go beyond a paywall to get access to those. But that's a really good resource, especially for folks that are new to ICP. It's really kind of a training ramp for folks that are really new to ICP and want to learn more about, what essentially is an interference on OES or mass spec, how do you combat it. We get into some really good detail about instrument maintenance. So lots of good stuff on there as well. And lastly, I want to put mine and Thomas's contact information on the screen. So if you have any questions at all, please feel free to reach out to us at any time. You can message us directly. We'll be happy to answer any questions you have. And I just want to thank you all for joining us this morning or this afternoon. And I want to thank our friends at CEM and Glass Expansion for inviting us to join this seminar. Again, if you're over in the European region, where this has been an all-day thing with those groups, I just want to thank our partners in that as well. And I hope you have enjoyed today's presentation. I hope you've learned a couple things you can take back to your lab. And again, if you have any questions, please let us know. And I hope you have a fantastic day. Thank you so much.